All right, notes 9.5 are an exponential decay. And if you look right here, you guys are used to seeing exponential functions appearing as follows. They'll look like this, where it starts off gradually and then it shoots way up like we have right here, okay? But exponential decay is just gonna work the opposite way. It starts off, decreasing very fast, and then it levels off right here. A perfect example of this is having medicine in your system. When you first have medicine in your system, you have a certain amount, and then it starts to wear off quickly, and then it eventually starts to level off, okay? So exponential decay, we're going to take a look at what we have right here. Question number 1. John bought a car for $15,000. As he drove it off the lot, his friend Riley told him that the car's value just dropped by 15% and that it would continue to depreciate, and this word depreciate means to decrease, 15% of its current value each year. If the car's value is now $12,750, according to, this should say Riley, what will be its value after 5 years? So question A, complete the table below to determine the car's value after each of the next 5 years. So let's see what they did here. Excuse me. So at the beginning, it cost $12,750 right here, right? So 15% of $12,750 we can calculate by just multiplying 12,750 by 0.15. So go ahead and try that in your calculator and see what happens. So if you take a look at what we have here, it's 12,750 multiplied by 15% or 0.15, you get $1,912.50. That's how much money you lose for the value of the car. So that's the depreciation of the car value. So right here, that's how we got 1912.50. Then if you were to subtract these two values from each other, you would end up getting this number right here. So let's go ahead and try that. So I would take $12,750 and I would subtract $1,912.50, and that's how you get $10,837.57. Now remember that what you need to do for this is you can just multiply 12,750 by 0.85, because if you're losing 15%, you have 85% left over. That's where we get this 85 right here. Press enter, that's how you get that answer. So you don't have to fill in this column right here to figure out the rest of your answers. But this is how much money you'll have after year 1. Okay, so the number of years passing since driving the car off the lot, this right here, this value right here is f of 0, but this answer right here is f of 1. So we need to figure out how to get the answer all the way up until we get to f of 5, because it says over the next 5 years. So figure out what f of 3 is, f of 4 is, and then f of 5. So we really don't need this bottom line right here. So right here, this is what f of 1 is. That's what it's equal to. And then we'll do our operation to figure out what f of 2 is. So I can just take $10,837.50, multiply that by 0.15 to fill in this value, and then subtract, or I could just multiply this by 0.85 right here. So let's try that instead. So I'm going to take 10,837.50, my answer, and just multiply it by 0.85, and then I get this answer right here, $9,211.88. So let's go ahead and fill that in our chart right here. So this would be $9,211.88. Okay, and then I would take that answer and multiply that by 0.85. So the next amount of money that I have is $7,830.09. Okay, so I'm going to go ahead and write out that that's my answer. Notice how I'm using the full value of my answer, and I'm not taking this 88 cents. I'm taking the full number that we have here, this 0.875. So that way I don't have any rounding errors when I do my operations right here. So it's $7,830.09. Then I can take that value and multiply that by 0.85, and that's how much I will have for the next year. Okay, so for the next year, I'll end up getting $6,655.58. So we can fill that in, 6655.58. All right, and then let's do it one more time to figure out our final answer, and we get $5,657.24. Okay, so let's go ahead and write that out. $5,657.24. So this is major. You start off with a car that costs $15,000, and after 5 years, it's only worth less than $6,000. So you're losing a lot of money right here. But if you were to graph this out as a function, which we will do in a little bit, you'll see that it's going to start off pretty high. It's going to decrease rapidly, and then it's going to level off. If you were to continue doing this, it's just going to 15% of a smaller number is just going to keep decreasing and decreasing and decreasing. All right. All right, so question B says, write an explicit formula for the sequence that models the value of John's car T years after driving it off the lot. So if you guys take a look right here, to figure out the first value, we took 12,750 and we multiplied it by 0.85. That's what we did here, and that's how we got that answer right there. Okay, and then we took that answer, $10,837.50, multiplied that by 0.85. So this is, you multiply by 0.85 once for the first year, twice for the second year, 3 times for the third year, 4 times for the fourth year, 5 times for the fifth year. So you would do it T times for the T year. Okay, so hopefully that makes sense to you, that we're just repeatedly multiplying by 0.85. So if I were to write it out as a function, I would say f of t equals, well, I start off with 12,750, and each time I'm multiplying by 0.85 to the t power. Okay, so then question C says to use the formula from part B to determine the value of John's car 5 years after its purchase. Round your answer to the nearest cent. Compare the value with the value in the table. Are they the same? So if I were to figure this out, I would figure out that t is 5, because that's the number of years. So 12,750 times 0.85, all raised to the 5th year, is approximately equal to, and I'm putting the approximately there because we're going to round. So let's type this in. 12750 multiplied by 0.85 raised to the 5th power, and you end up getting the exact same answer, $5,657.24. So let's go ahead and write that out. And this is a 7 in case you can't see that that's a 7, and $24. So they are the same value, and that should make sense to you. But it's much easier to use the explicit formula as opposed to recursively figuring it out and multiplying by 0.85 repeatedly. So question D says, use the formula from part B to determine the value of, let's say, John's car, not Malik's car, 7 years after its purchase. So let's figure this out. I would say f of 7 is equal to 12,750 times 0.85 to the 7th power. Okay, so I'm going to do the same thing here. So I don't have to type it all in again. I'm going to highlight this, press enter, and then I'm just going to delete this 5 and make it a 7. Okay, press enter, you get $4,087.36. All right, so let's go ahead and write that out. $4,087.36. So how is exponential decay like exponential growth? Well, if you remember, we said that the general equation for exponential growth is a times r to the x power, where a is the initial amount, right, and r is the growth ratio. Okay, but when it's growth, r has to be bigger than 1. When it's decay, r has to be less than 1. So if you notice in this example right here, our r value is 0.85, so it's getting smaller and smaller and smaller. in the previous examples that we did before. For example, if you look at the previous page, question number 8, for example, our R values that we were comparing were 1.07 versus 1.05, but they were both greater than 1, okay?
Except it has, it is the same. That's an it, not an H. It is the same, except the growth factor is less than 1 as opposed to greater than 1. So B would be less than 1. And remember, if it looks like this, let me draw that a little bit better. If it looks like this, it is exponential growth. And if it looks like this, it is exponential decay. All right? Now, you may be surprised to find out that exponential growth and exponential decay occur all the time in real life, like times that you probably don't even realize. Even, for example, those of you guys who have been following March Madness, the way that the teams are eliminated is by exponential decay, because you start with a large amount and you are decaying by 50% in each round. All right, so let's go ahead and take a look at question number 2. Identify the initial value in each formula below and state whether the formula models exponential growth or exponential decay. Justify your response. So in question A, our initial value, our starting amount, is going to be this 2 right here, because that's the A value, it's your starting amount. So we're going to say that A is 2. And then I have to look at the B value. Now, is the B value greater than 1 or less than 1? If it's 2/5, it's less than 1, so that means that it's going to be exponential decay. And then our reasoning for it is that B is less than 1. Okay, so let's do question B together. In question B, our initial value is 2/3. Now, our initial value has no effect on whether or not this is exponential growth or decay. It all has to do with this term right here, this B value. So this B value is also less than 1 again. So we're going to say that this is decay. And the reason why is because B is less than 1. Go ahead, try C, D, and E. See how you do. And then come back and compare with me with your answer. Don't forget to press pause. All right, go ahead, compare C, D, and E with my answers. For C, you should get that the initial value is 2/3, and it is exponential growth because B is greater than 1. For D, you should get A is 2. It is also exponential growth because B is greater than 1 again. And then for E, it is the initial value is 3/2. It is exponential decay because the B value is less than 1. All right, here's an example of a real-life situation in which exponential decay happens, just like the example that we looked at with the car's value depreciating. When you take medicine, the amount of medicine that's in your body decreases by a certain factor, and so after a while, it'll eventually taper off. So let's take a look at question 3. Kelly's mom takes a 400 milligram dose of aspirin. Each hour, the amount of aspirin in a person's system decreases by about 29%. How much aspirin is left in her system after 6 hours? So we're going to use the exponential decay formula. So the initial value is 400. Now the question is, what is the B value? Well, the B value is how much it's decreasing by. So it's going down by 29%, which means that there is 71% of the medicine left in your system, which is 0.71. So this right here is your B value, okay? So I'm going to say that the answer, or the formula, is going to be 400 multiplied by 0.71 raised to the t power. So I'm going to figure out what f of 6 is because it asks you after 6 hours. Okay, so it's 400 multiplied by 0.71 raised to the 6th power. Go ahead and plug that into your calculator, and you will see that after 6 hours, it goes from a whopping 400 milligrams to just 51 milligrams because, again, it decreases pretty fast at first, and then it starts to taper off, level off. Okay, so your answer to this question is 51 milligrams. All right, number 4. According to the International Basketball Association, a basketball must be inflated to a pressure such that when it is dropped from a height of 1,800 millimeters, it will rebound to a height of 1,300 millimeters. So Luke decides to test the reboundability of his new basketball. Let f of n be the height of the basketball after n bounces. Before we do this, I just want you to realize that if the basketball drops from a certain height, eventually, the rebound height will get shorter and shorter and shorter, and if you're to map it out, it looks just like exponential decay, which you will see shortly. So let's look at question A. Assume the ratio of each rebound height to the previous rebound height remains the same. What is the ratio? So I'm going to take my current rebound height, which is 1,300, and I'm going to do it as a ratio to my previous rebound height, which is 1,800. So that means that my ratio in simplest form would be 13 over 18, which hopefully you will recognize is the B value because this is your growth ratio, okay, or your decay ratio actually. All right, so question B, complete the table below to reflect the heights Luke expects to measure. So I would take my first value, which is 1,800, and I would multiply it by my ratio. So if you multiply 1,800 by 13 over 18, you'll end up getting 1,300, which is what the height would be after one bounce. Okay. Then to figure out the next one, I would take 1,300 and I would multiply that by 13 over 18 and see what I get for that. And when you multiply that value, you'll end up getting 939 right here. Okay, so this right here would be 939. Then you would do the same thing for the third bounce. You would take 939 and multiply that by 13 over 18, and you would keep going. Go ahead and fill in the rest of the chart, press pause, and then come back to me to see how you did. All right, so these are the values that you should get. You should get 678, and then you should also get 490. All right, and those are all measured in millimeters. So question C says, write the explicit formula for the sequence that models the height of the basketball after any number of bounces. So remember, you're repeatedly multiplying by 13 over 18 right here. So this value right here is what is your, remember we said is your B value, it's your growth value, and think about what your initial value is. What I want you to do is try to write it out yourself, and then when you're done, compare with my answer to see how you did. All right, you should get that f of t is equal to the initial value, which is 1,800, multiplied by the growth ratio, which is 13 over 18, all raised to the t power, because you are repeatedly multiplying by 13 over 18. Question D asks you to plot the points from the table, so we'll go ahead and do that. So I'm going to take my first bounce occurred at 1,800, so I'm going to put a dot right at 1,800. Excuse me, it started at 1,800. It was not after the first bounce. After the first bounce, it was at 1,300. After the second bounce, it was at 939. Okay. After the third bounce, it was at 678. After the fourth bounce, it was at 490. And you know what? I would like you to try a couple more bounces, see what you end up getting. So go ahead and go up to maybe the sixth bounce, see what you get. So I got that after 5 bounces, the height would be 354, and that after 6 bounces, the height would be 255. Okay, so I'm going to put a dot right at 354. And then I'll put another dot at 255. Okay. So if you notice, it definitely appears to have an exponential decay pattern as you graph this all out. All right. So the question is, or the last question that we have is asking you to use the curve to estimate the bounce number at which the height will drop below 200 millimeters. So go ahead and take a look and see what you get. Where do you think it'll drop below 200 millimeters? Write down your answer. So I'm going to guess after 7 bounces that it will drop below 200 millimeters. And it's just a guess based on my graph. So then I'm just going to check to see if it works. So I'm going to figure out what f of 7 is. So I'm going to take 1800 and multiply it by 13 over 18, all raised to the 7th power. And then I will see what that will give me when I plug it into my calculator. And you will get about a height of 184 millimeters, which seems to be the bounce number that will get you to drop below 200 millimeters. All right, hopefully that all makes sense, and I will see you next time in class.